start the recording. That means Happy Garbage Day! Welcome back. I hope everyone has their snow shovels, car scrapers, blankets, and grocery store runs done, because we're apparently going to get dumped on tomorrow. So, boots, also winter boots.
How many inches are they anticipating?
A lot.
All I saw was like snow all hours.
Yeah,
all up to your knees.
it's a warning
my knees,
now,
yeah.
not a watch, so
Oh. Knees. Yeah.
we will make that work. So what we have on tap today then, Bladimir is going to discuss formative assessment number 1. He made slides.
Ooh,
So
he's
if-
prepared.
He is. If you'd like to have the slides, I can put them up after class, if folks think that would be helpful. You have, in the meantime, next Monday is the second bridge activity, covering interaction terms and standard regression, and then extending into the Logit world that we're getting acquainted with. And in case that wasn't enough, if you need more in your lives, homework 1 is available. It's about the models we haven't seen yet in terms of the handout and the examples, so it's a bit early, but he checked it, said it was good, so he's ready to help
Thank
you
you.
whenever you want to get to that. That's not due for 2 more weeks or so yet, so we got some time there.
Mm-hmm.
But in the meantime, we've got formative assessment number 1. I will turn things over to you. I will operate the waiting room if
Thank
need be,
you.
but you just want to keep an eye on the chat.
Yes.
And make sure you're in the frame because you're tall.
Yep.
There we go.
Don't worry.
Oh, he adjusts.
I like
it.
this desk.
Yeah.
Yeah.
Hi, people on Zoom. Hope you are doing well. Hi, people in classroom. I hope you are doing well too. Thank you, Lisa, for this time. I know that you are here because of Lisa, but today I will take a couple of minutes to discuss the questions that you answered for our formative assessment 1. Thank you for your time. We read all of your answers, so the material that I created is based in part on your answers, and it's also based on Lisa's materials and some things that I believe or I guess that can help you to understand some of the points that we are trying to make here. As Lisa said, well, here, yep. I will be using this set of slides so you can have access to this later. And short story, I created slides, well, because last semester for another course in which I was the TA, one of the students asked me, why don't you are using slides when you are talking? And I say, yeah, that's a good idea. So you have slides because of that student's idea. Thanks to her. And why slides? I don't know what to use. Slides are formal, right?
Yeah.
So that's because they are slides. So, question 0 is, I will be reading the chat, people on Zoom, so you can participate too. Question 0 says, are there any topics that we have covered so far that you would like to review more in class? We had some answers. For this specific question, I would like to highlight 2 things. One of them is link functions, the other is centering predictors. I read some questions related to these 2 things, so I prepared some slides that maybe can help you to get some ideas about this. First of all, link functions. This is based on our lecture 2. You can see that this is the slide 3, so you can go back to that slide. The link function is just how the conditional mean, what the model is predicting, is transformed. So the model directly predicts an unbounded version of that outcome. When I was thinking about this, I remember that 2 years ago, this was pretty challenging. So to me, was useful Agresti chapter 1. I read that chapter like 3 times because it's useful, I think, to understand some of the machinery behind GLMs. I think that this description is helpful. The link function connects the random component with the linear predictor. Here, I try to translate these 2 concepts because the random component in Agresti, for us, is just the conditional distribution of the outcome. For example, when we have a binary logistic regression, the Bernoulli distribution for our binary data, that's the conditional distribution. Then we have the linear predictor, which is the model. This is a simplification because this part would be the model. We are combining a set of predictors and its fixed effects to have some prediction about the outcome. To me, this is the key part to understand the link functions, because normally what the model is doing is taking the linear combination to predict something. This is eta, if I'm not wrong. However, sometimes we cannot have the variable by itself in the model. For example, when we have binary data, we have zeros and ones, but we are predicting something continuous in the model. And zeros and ones are not continuous. However, we can predict probabilities. And how can we transform those probabilities? Using logit, the logit link function. So the model, the binary logistic regression model, will be predicting not the zeros and ones directly, but the link transform conditional mean, which is in logits. And this is the relationship that we can find in Agresti. What the model is predicting, or is supposed to be predicting, is the linear version, well, not the linear, but the link function of that outcome, the link transform conditional mean. I know that this is hard, so questions? Something that's not clear yet? Mike?
Yes. So when in R, I'm running my linear regression, okay? I know I'm not using the zeros and ones anymore. I know that. Okay?
Yes.
If that's my predictor, that's what I'm predicting. Okay?
Yep.
So instead of the 1, for example, okay, I would be predicting using the logit for the 1. Is that correct? For that, or no? And if not, what am I using in my model? You know, to get what am I using for my outcome over here? My dependent. What am I using for my dependent variable when I run my regression model?
Yep.
What was that exact value?
Can I rephrase that into what do we have in our model? What do we have in our data? Is that precise enough?
I think he's
Because-
asking what your outcome is.
Yeah. So
Okay.
so yeah. What's my y?
What's the y? What's the outcome?
What is my y
Yeah.
when I run R?
Yes, is this part of the slide. What you have in R specifically, what you see under the fixed intercept, that value represents the expected value in logits. Whatever the one is, let's say that one is the probability of success in something.
Call it 70%.
So, yes, let's say that's 70%.
Yes.
But in R, you will have the logit version of the 70%, which is the transformation. That's in one of the slides. Lecture 2, you have that. Because we are taking the log of the odds of the probability of a 1.
Right.
Yes. So in R, directly from a summary statement, for example, from the summary function, the summary of your model, what you have, that model is in logits. That's the log of the odds of the
Right.
probability of a 1. So if you take the exponent of that number, you will have the expected mean of the outcome in your data.
Right.
Yes.
Okay.
Is that enough?
Better.
Okay.
Yeah, we'll keep going over.
Rebecca.
Yeah. That's it. Better.
Yes.
I have a question as well, and it's going back to the definition of religion. It's the law of the odds and the probability of one.
Yes.
And I'm trying to understand the meaning of this one. Because if you're looking at like binary data, then the law of the odds and the probability of the one is going to be different. Like it's much more likely that you would get a one if the only options are 1 and 0. But if you have like continuous data, ranging from, well, continuous data would truly be unbounded. Like, the probability of getting a 1 in a continuous data set would be much lower. So I'm trying to understand, like, what does that 1 mean? When we say the law of the odds of the probability of 1, is it the probability of the 1 in the continuous data, or whatever your, like, model variables are, or data variables are? Or is it the log of the odds and the probability of a 1 in the Bernoulli distribution, or maybe just other ones?
Yep. So can I rephrase that?
Yeah, anything.
What's the one?
For the recording, too.
What's the one in in the binary logistic regression?
In the definition of a logic.
What's the one in the definition of the logic in the model? Yeah, that's related to the variable we have, because when we have continuous data, we can have something between negative infinity to positive infinity. So we are not predicting one directly. We are predicting something, in this case the mean of whatever we have that's continuous. However, when we have binary data, what we have is zeros and ones. Then the Bernoulli distribution, what defines when you look at the formula, is the probability of a 1. That's the parameter of the distribution. That's why what we are predicting is a 1. And that 1 is just what we have in our data, can represent any type of thing. That depends on you.
So in the definition of a logic, the one comes from the Bernoulli distribution.
Yes, because that's what we have in our data. What we are taking when we use the link function, what we are taking is the probability of a 1. We are not working with ones directly, but with the probability of 1. So that's why when we have odds ratios, the scale goes between 0 and positive infinity. Because if you look at the ratio, that's the probability of 1 over the probability 1 minus the probability of 1. So that ratio is then converted into logits to try to have something unbounded, which is in the logit scale, which 0 equals odds ratio of 1.
So we would use this in situations where the data variable that we're trying to predict is binary, but we don't have a good statistical model for dealing directly with binary data, so we transform it into the logit, and then we do the predictions on the logit.
Yes and no.
Oh,
What? Yes. Yeah. When we have binary data, when we have binary data, we can use the logistic link function. That's one option. We could also use probit.
Yeah, we've got there yet.
Oh yes. So one option is to use the logistic link function to go from zeros and ones, or the probability of 1 in the Bernoulli distribution, to something unbounded in the model. Remember that we have the model scale and the data scale. We are not transforming our data. Okay? We are not taking our zeros or ones in the data, creating the logit and using the logit in the regression. We have our zeros and ones in the data. The model inside the machinery is transforming those values, is transforming the conditional mean that's being predicted by something unbounded based on the link function we are using. Could be the logistic one or probit, but we have zeros and ones in our data. The model, however, will be working on a different scale based on the link function that you are using. Logistic or probit or log. Is that clear? Does it help?
helping a lot, yes.
Yeah?
It's clearer.
Awesome. Devin, do you?
Yes, can you say more about the conditional data, conditional mean?
Yes,
The function it serves in logic?
of course. The conditional mean is what the model is predicting. Well, however, the model won't be predicting the conditional mean directly. We'll be predicting the link transform conditional mean. Why? Because the original conditional mean in the case of binary is the mean, but the mean is bounded. So we cannot predict that conditional mean. However, the link transform conditional mean with logit or probit can be something unbounded. And that's the model scale, different to data scale, which is zeros and ones. We are not changing that. Does it help? Awesome. Yeah, I think that there is a slide with this. Sorry,
Yeah, there'll be several. I'm trying to think of a real world example that can map onto this too. So let me let that percolate. We can probably keep moving on.
yes,
The century one, the other stuff too.
yes. Question?
Well, unfortunately, it's the same thing. I just wanted to know on this slide slide that
Yeah.
shows the bounded and unbounded, if I'm understanding it right. Like the first one, the predictor goes beyond 0 and 1, so we use the logit to get the probabilities within 0 and 1. Is that what that is?
Exactly.
Okay, and then you use the reverse link to transform it back to.
Yes.
But those are the probabilities.
Yes, exactly.
Okay.
Because yes, that slide is good because we know that in terms of probabilities we have boundaries. We have zeros or ones. However, if we draw a line, we have things out of those boundaries, and we cannot have something below 0 or something above 1. It doesn't make sense in that scale, right? However, when we take the logit, that linear slope now can go out of the boundaries, but that's in the model scale. When we take when we apply the inverse link function and we go from logits to props, you will see that we have something like an S, because now the lower values can go below 0 and the upper values can go above 1. Right? Awesome. Thank you for your questions. And let's go to the other thing was about centering predictors. Why should we center predictors? Two main reasons. First of all, because that will help us to have an interpretable intercept. Remember that the fixed intercept is the expected value of the outcome when the predictors are 0. So if we have something that makes sense for those zeros, that's better. The other thing is because when we have interactions, the simple fixed effects of the predictors involved in the interactions will be conditional on the other values on the values of the other predictor being 0. So in that case, you will see that's helpful to center your predictors at something meaningful. So those are the two main reasons. Questions?
I wrote down all the questions that you all put in that answer, so we'll get through them as we go, through those topics.
Yep.
I've got
People on
thank you
Zoom,
for getting started.
you can write down questions too. So then, question 2 was this one. Or question 1. Imagine you are reading the following comment in an online forum in response to a question about whether one should use regression or ANOVA. Regression is for prediction, whereas ANOVA is for testing mean differences. How would you respond to the original question and the comment? I tried to summarize these things later, but first I think that this slide, the slide 16 in lecture 0, could help us to understand that ANOVA is a special case of the general linear regression we are covering in class. So now, the context across the areas or disciplines can be different. For example, in the context of design of experiments, when we talk about ANOVA or analysis of variance, we are talking about a model in which we try to explain variance with the factors we have in the model. Factors is the same as predictors. However, in other contexts, for example here, we talk about ANOVA when we have certain kind of predictors, categorical predictors, for example. And we can have one-way ANOVA, two-way ANOVA, or ANCOVA models when we have categorical and continuous predictors in the model. So, I try to summarize some of this answer with some of your comments. ANOVA is a special case of regression. I think that's what we are discussing here. The choice depends on the specific research question and the type of data. Here I would say the predictors specifically that we have. And I think those two things summarize this question. In addition, I like this answer. You can get the same information from a regression or an ANOVA, so it doesn't matter which you run. I like this one. Because at the end of the day, with both models, you will have the same information, but again, the context and the use of both can be different across areas. And I know that some textbooks try to make this difference between explanatory and predictive models. So maybe the explanatory models are like the ANOVA ones, and the predictive ones are regression. But at the end of the day, if I show you an equation, for example, you couldn't see the difference between an ANOVA and an one-way or two-way model because they are the same. Well, they have the same structure. That's my point. Finally, Lisa's comments. Thank you, Lisa. Both are used for prediction, but with different kinds of predictor variables. Questions? Something that you would like to hear again? For this one? Okay, so we can go to the next one. The last three, this will be quick because most of you had this correct. So good job. Remember that Lisa uses the three-step approach for interactions. First of all, we select those terms that include the slope we are interested in. Then we factor out the repetitive things, and then we get our solution. So, in this specific case, for example, what's the GS slope for someone with an F equals 2 having this model as reference? We know that the GS slope, not the predicted value, but the slope, okay? The GS slope is here, B2, and then here, B5. So then we take these terms, we factor out, in this case, G. Yes, so we have beta 2 here exclusively. And we know that F would be equals 2, so here this is F equal 2. And here is equals 1 because we are taking the slope.
It's been factored out.
Yes, it's been factored out. So that would be question, I think that is question 3. Well,
Well, this is a question.
questions?
Just one.
Yeah?
The parentheses 1 after beta 2.
Yep.
Is that needed or not needed?
Not needed.
Yeah.
Not needed. So for example, if I were to say just beta sub 2 plus beta sub 5 times 2, that would be fine. Okay.
Yeah.
I just want to make sure I'm. Okay.
Yes.
Yeah, this is the multiplier that would be in front of G in the combined equation.
Right.
Yep.
G can be whatever it needs to be.
Exactly. Yeah. In this case, it's 1 because we are having that as reference, and we are modifying the slope of F. In this case, with a 2. Then we have question 3. So now we have these values. G equals 3, H equals 4, and I equals 5. Again, from the formula or from our model, we take all of the slopes involved in what we are doing. So now, this is interesting because I equals 5. Do you think that this is important to get an estimate of the F slope? Doesn't matter? No, it doesn't. Why? Because as we can see in our model, I is not being involved in any of the interactions with F. So it doesn't matter what value we have there if we are interested in the F slope. So again, we select our betas here. So for F, we have beta 1, we have beta 5, beta 6. Then we factor out the F's. Yeah, I did it here, but not here. That should be empty.
You can fix the slides and send them back.
Yes.
That was my question. Really? Okay.
Yeah, we don't need the ones.
Yes. So here we have then the values for G and H. And finally, this is a tricky one. Because now, what would be the I slope when we have F equals 2, G equals 3, and H equals 4? The I slope would be just the slope. Why? Because I wasn't included in any of the interactions. So whatever that fixed effect is whatever the slope is, it is what it is. Won't be affected by any modification on the other variables because it wasn't part of any interaction. Yes, it is marginal. Not a simple or conditional marginal. So, that's all I think. Questions, things, well, comments, opinions, impressions. Was it okay?
Thank you.
Awesome. Thank you so much for your time. I will fix the slides and I will send them to Lisa so you can have access.
Hey, I want applause. Yay! Dang, you really are tall, dude. There we go. That's more like it. There we go. And I'm sitting down, because otherwise my shins hurt after standing for 3 hours because I'm a wuss. So, yes. So thank you for that, Bladimir. I was also going to say I had fun this morning building a playlist of your theme songs. I put the link to that playlist in an announcement in Icon, so you can check that out. A little bit of overlap, but interestingly, most folks pick something new. I added my choice for the semester, which I have decided for both classes is going to be Staying Alive.
I wonder who's that one.
I mean that in every sense of the word. We're going to try to stay healthy. We're going to try to stay out of a blizzard. We're going to try to stay sane. We're going to try to stay in business, in science, in research, and all the things. We are going to stay alive. That is what we are going to do. And yes, that song just rocks anyway, so it's a classic. All right, I think that was all I was going to say about that. I do have a new example we're going to start today, and then a one for ordinal, which is the same idea as these models, but building on it a little bit of complexity. Let's see, let's get rid of that. And it looks like I don't have my other files open. I got a little bit distracted ahead of time, so 1 second, folks. Let me get example 2A open, and lecture 2 is what I'm doing, if you'd like to play along. Here we are. I think seeing numbers will make this better, because the idea of links and stuff is very, like, it's very abstract. It's difficult to understand. And if you're feeling like I don't get this, yeah, welcome to the club. Like, it's not easy. But the big picture here, let's go back over what is a logit again. We'll do that stuff here. So the idea is that we are predicting what statisticians would call the expected value of an outcome, or what I would call the conditional mean, meaning what is the expected value based on your pattern of predictors. In regular regression, I just sort of skip over all of that because it's not really necessary. We just go, I'm predicting y, like the end. But no, we're predicting the expected value of y, which happens to be the mean given a normal distribution. For other kinds of variables that aren't normal, we have different types of expected values. For binary, for a column of zeros and ones, the expected value is the proportion of people who got a 1, the probability of a 1 for any given person. Like if I don't know anything else about you, I would just have to say, well, 60% of the class got a 1, let's go with 0.6 for you, because that's a reasonable thing. So we can predict probabilities of a 1 ranging from 0 to 1, and they are truly continuous in that interval. But we can't fit a linear model to predict probability directly, which is what we would do if we put it in a standard linear regression, because the model needs to understand that the predicted outcomes can't go past 0 and they can't go past 1. We got to solve that problem. So we solve it in 2 steps. So first thing is we turn probability into a quantity known as odds. That is the probability of a 1 divided by the probability of a 0. So here's an example. If the probability is 0.7, then the corresponding odds of that probability of a 1 are 2.33. If we want to solve for the odds of a 0, that's 0.43. So this, as an outcome to be predicted, is halfway there. It's unbounded on the positive side, but it's still bounded at 0. So some genius figured out that if we take the natural log, not log base 10, mind you, but natural log, and then we have this thing that is called the logit, or the log odds. Depending on your field, one of those may be more comparable, or more comfortable. So then if we do this, the probability of 0.7 translates into a logit of 0.85, whereas the probability of the logit being 0, meaning a probability of 0.3, that translates into negative 0.85. So logits are a metric that are they are they are symmetric, that's the word I wanted, symmetric at 0. So a logit of 0 corresponds to a probability of 0.5. So the model is going to predict logits. That's what it predicts directly. And we have to back translate logits into probabilities through an inverse link. So you will hear me say the word back translate or unlogit. That's what I mean, inverse link. So to answer your question before, like what is R operating on? Your model statement will look the same, Y tilde predictors.
Okay.
But then you'll say somewhere in the code, use a logit, and it will know to turn that probability of a 1 into a logit metric with which to be predicted. So
I'm not making any columns or anything.
No, you literally can't turn a 0 and 1 into a logit.
Okay.
So if you feed it into this formula, let's say that everybody got a 1.
Mm-hmm.
So I have the probability of a 1 is 1, divided by the probability of 0 is 0. 1 divided by 0, good luck with that. Undefined. If I flip it, if I have all zeros, so I'd have 0 over 1, okay, so far so good. Can I take the log of 0? Also undefined. So you literally can't take a transformation of 0, 1 using a logit link, like directly as a data problem. What you're transforming is the probability of a 1. And you won't know that until you figure out what the model says it should be based on your pattern of predictors. So a logit is the log of the odds of the probability of a 1. And I say it that way so we hit all the points in between. You will hear the phrase model scale and data scale referred to throughout the semester. In binary data, data scale refers to probability. Like that's what we're trying to predict. At the end of the day, I want to know what is a given person's probability of having a 1 instead of a 0. In logits, that's model scale, that's how it happens. So in this graph, which is mapping showing the nonlinear transformation between probability and logits, a data scale probability of 0.5 goes with logit 0, and logits are symmetric as you go up or down. So if I know one of these things, like a probability of 0.99 is a logit of 4.6, that means the corresponding probability of 0.01 has to be negative 4.6, and that will come in handy. So this is your first exposure to the idea of a link function. This is a brand new concept. We're not transforming data, we're transforming the expected value out of the model. Here's another picture that shows the nonlinear aspect of it. So changes in logits will have the most impact on probability when it's in the middle. As you get further and further towards the probability boundaries, corresponding changes in logits become decreasing changes in probability. So your predictors have the biggest job to do towards the middle in probability metric. The middle point of odds is a weird thing for binary data that doesn't show up in other kinds of data necessarily, just categorical data. So it's somewhere between data scale and model scale. But the neutral point, a probability of 0.5 corresponds to an odds of 1, so that's 0.5 over 0.5. And then if you take the log of 1, that's 0. So a logit of 0 is a probability of 0.5. That's what we know. Okay, let me see what we did. We did this, 3 different versions of the model. Do you want to see an example?
Yes.
Yes. Like, oh, please, God, stop talking. Okay, so we're going to have to, if you want to do that, then we're going to have to skip around in the example a little bit to skip over the things I haven't talked yet. We're cool with that? Okay, all right. They're just so grateful to see numbers. I love it. Okay, so this example, I stole the data set from the UCLA help pages and used it for this example. It's public data, and I'm pretty sure it's fake data because
So therefore it's not stolen if it's public.
yeah, I stole fake public data is what I did. By the way, this website, this is a great resource. They have a ton of examples of how to do lots of stats things in all different packages, and it's all like written out with explanations and code and stuff. It's a very good website. But I don't deal a lot with categorical data in my world, so I had to go find some, so I did. So the original version of this example is actually an ordinal outcome. I turned it into binary, and we'll do it as ordinal subsequently. So we're going to demonstrate what is known as logistic regression. That phrase means I am using a logit link function to transform my probability into something continuous, and my distribution instead of normal for the data is Bernoulli. Bernoulli meaning only two choices. So it's a discrete distribution rather than a continuous one. And Rebecca, to your point earlier, like the probability of exactly one in a continuous distribution is undefined. You can only have a probability of exactly this answer in a discrete, like categorical distribution. So this is like the probability of anything is not something you're ever having had to think about before. It's new. Yes, sir.
So your discussion of like binary outcomes and then continuous data is confusing me. How does those things relate in the situation?
Okay, I just realized I lost my water bottle, so one moment for that. I can't get through class without drinking. Are you kidding me? No, I swear it's just water. I promise. Okay, what is confusing again? Can you please repeat the question?
We're talking about binary
Yep.
outcomes, right?
Yes.
But you're saying that they can be turned continuous. Can you say more about that? How you go from?
Okay.
I'm not understanding.
Yes. You cannot take a variable in your data set that is zeros and ones and turn it into anything continuous. You cannot do that. That's not possible. But I think she was trying to draw the parallel with regression models that normally predict continuous outcomes. That's what like the general linear model class would have had, and other departments like their first semester stats sequence would have focused on that. Those models are designed for outcomes that are conditionally normal, meaning the residuals are normal after you predict them with whatever you put in your model. That is supposed to be a continuous outcome. It's supposed to be unbounded, so you don't have to worry about the predicted outcomes going out of bounds because there aren't any. And it's supposed to have a normal shape to it. So we are using regression models for a different kind of outcome right now that is binary, others forthcoming. But we're still having any kind of predictors. But because the outcome is binary, we got to worry about boundaries for its probability, and we got to worry about residuals not being normal. So we say, okay, they don't have to be normal. We'll make them Bernoulli instead by switching it out for that distribution. So when you say you're doing logistic regression, that is what you're saying. Like think about the Legos, right? I want you to know the pieces of how this stuff fits together, because then you can custom design your own Lego house as needed. The link function is the logit, the distribution is Bernoulli, and the linear predictor is whatever predictors you put in the model. That's a choice you get to make. There are other links. To the best of my knowledge, there are no other distributions other than maybe extreme value, but that might even be like a special case of this somehow. So that's beyond my pay grade. I'm not going to worry about all the distributions that are out there. If you want to know about that, go over to the stat department. Okay, are you with me so far? We're predicting in this thing whether or not a student is decided they want to apply to grad school. 0 is no. Greater than 0 is pry. This is shorthand Midwestern slang for probably. Yeah, I'll probably go to grad school. We'll see. We are going to be using undergraduate GPA, which is on a 4-point scale. I'm going to center that at 3, because a GPA of 0, while technically possible, is not going to be observed in a sample of people who are considering graduate school. If you have a GPA of 0, it's not going to go well. Can you even have a GPA of 0?
Not in graduate.
Not in graduate. Well, there you go. You're not going to graduate school for other reasons then, if that's the question. So this is a continue-ish predictor, I would say. It's numeric, but it has boundaries. But it's a predictor, so we're not going to worry about distributions for it. And then 2 binary predictors, whether or not one of their parents has a graduate degree, which might make someone more likely to want to go to graduate school, and whether or not they attended a private undergraduate university, which also might be the case. So I'm going to ignore this much for right now. Okay. This data set, I had to do relatively little to prepare it. The only thing that I needed to do other than import it was make a new predictor. So reiterating the review that Bladimir provided, I am centering GPA at 3 because I want my fixed intercept to mean something. If I left it alone, my fixed intercept would describe the expected probability of wanting to go to grad school for someone with a 0 GPA. Weird, unhelpful. So now this is the probability of someone wanting to go to grad school whose GPA is 3, B average. Not a great average for some programs, but possibly for others. You never know. And I am selecting all the rows that are complete, because if I don't, they will get dropped out anyway. So I'm doing that ahead of time to sort of point that in terms of your lives, things you'll have to think about. And if you're like, isn't it bad to delete rows that are incomplete? Sure it is. But that's not this class. That's another class. It's on Wednesdays. Right, Bladimir? Yeah, he's in that class. So in Stata, to make a new predictor is a gen statement where I say new equals old, okay? So note that I have renamed it GPA 3 so that I don't overwrite that column. If you put the same name in both spots, every time you run this code, you're going to subtract 3 again, and again, and again, and it's going to be like very, very far away from what it was initially. You don't want to do that. So we're going to make a new name. My naming convention is I stick the centering constant at the end so that I know where it's centered and I don't have to think about it. So GPA centered at 3 is what this means to me. You can choose your own conventions for naming things. Just try to be internally consistent would be my advice. In R, we are also reading in the data from Excel, and I'm doing the same thing. So I'm only going to use base R for data transformations in this class. If you know and love the tidyverse, Godspeed, but I don't. So my code is designed to be as easy to read and follow as possible. That is why I'm picking this. So example 2 is the name of the data set. The $sign delineates where the name of the variable column starts. So then it's column named GPA 3 in this data set. Stata only lets you work with one data set at a time, so you don't have to go through that extra layer of saying which data set you're operating in. And I am then filtering just for columns that are complete, and I'm doing an extra step to compute correlations that we're not going to talk about right now. But we are going to talk about descriptive statistics. So in this hypothetical sample of exactly 400 people, again, what are the odds? Yeah, the mean of this variable is 0.45. So that means that 45% of the sample said, yeah, I might go to grad school, and 55% said, nope. We need to know this. This will help us make sure we know what our model is doing, because that is step 1, is figuring that out. Okay, skipping correlations, we're not talking about that, we're not talking about that. Here we go. Okay. Yeah, we're going to run correlations, but it's a new kind. We're not there yet. Let me back all the way out of here. Okay. So first thing we're fitting is an empty model. Do you remember what that word means?
No predictors.
No predictors. Now, why am I doing that? Nailed it. For each of these, I'm going to try to give you a research question. Here's mine. What am I predicting? That's my research question right now. It's a good one, right? Before you know anything else, you got to know which way is up. What is being predicted? Because certain software for these models defaults to predicting the probability of a 0. Some software defaults to predicting the probability of a 1. And not all software is adequately documented. So I'm going to figure this out through brute force. So this is not just pedagogy. This is literally me checking to make sure I know what it's doing. Especially in R, this is necessary, since there's a whole bunch of different packages that do similar things. So what I am predicting, the left-hand side of the equals here is the log of the odds that apply to is 1. So apply to is the name of the outcome. It's called 2 because there's only 2 possibilities. When we model the ordinal one that has 3 possibilities, I'm going to name it apply 3. So we keep straight. So you can kind of shortcut this like this. I don't know if this is kosher to do, but I've done it. Let's put it that way. So this is like a shorthand for this. Doesn't really save a lot of space though. And I'm saying the only thing in the model is beta 0. That's my fixed intercept. That then, if I want to go back to probability, here's my little equation. Commit this to memory. E to the predicted logit over 1 plus e to the predicted logit. That's my inverse link that goes back from logits to probabilities. The good news, you don't have to do any of this math yourself. The computer will do it all. So here first is Stata, then I'll show you R. The command in Stata I'm using is called logit. Guess what it does? Logistic regression. Pretty straightforward. So Stata, like R, is built of a bunch of little routines that do very specific things. There are more general routines that you can use for this, and I'll show you those later in the semester when we need them for certain things. But this one is very straightforward because it's built specifically to do binary outcomes using a logit link and a Bernoulli distribution. So all I have to type, other than a title, this is optional. This is me just labeling what's happening. Logit, here's my outcome, comma, which separates out options from instructions. No log means, you know that iteration history that like fills up the screen? Just don't print that. I don't need it. You might think, does this mean don't log it? No, don't show it in the log. Not the natural log, the output log. So it's going to give me a couple things here that are relatively of interest, but not absolutely, meaning log likelihood. My log likelihood for this model is minus 275. Is that good? No. This is the sum across persons of each person's individual height of their data in the log metric. So we take the height, we log it, we add it up because people are supposed to be independent. So this is how tall this model made my data collectively. So this number has no absolute meaning, but it has relative meaning because what we're going to do is add predictors and see if it made the data taller. Okay? So it tells you this. This is now going to be the basis of your new thumbprint for the answer keys in homework. So I am going to ask you for a quantity that is this number, log likelihood, times minus 2. The reason for that will be apparent soon, but just trust me, there's a reason. I don't want you to have to get out your calculator to figure that out. So there is a command that says, can you take the number that you just printed and multiply it by 2 for me? And it says, sure I can, and then it prints this out. So this little piece of code you can reuse throughout the semester to turn log likelihood into the minus 2 version that you'll need for your homework. If this number is correct for your model, and it will be the first question on most models, you know you have the right ingredients. You don't have the right outcome, you have the right predictors. Previously, in regression land, using normal outcomes, I used residual variance to do the same thing. Now we're switching what it is. Okay, next thing of interest. Const. What's that mean?
Constant.
Constant. But
Y-intercept?
the intercept, yeah. I actually really hate that it labels this because all fixed effects are constants by definition. They're not variables. So the constant is sort of ambiguous. But stata means intercept. So the intercept is minus 0.2, excuse me, minus 0.2. And you're like, I thought we were predicting the probability of going to grad school. Not directly.
Not with our model.
What are we predicting instead? Yep, I forgot my conductor stick. But I've got the other one. The one that somebody bought me. Here we go. The law of the odds of the probability of a 1. There we go. Commit that to memory. That's what we're doing. So the logit, on average, of someone deciding to go to grad school is negative 0.2. Now, I don't know how much that is. I can't do the math in my head. But I can tell you that it's negative means what?
Less than 0.5?
Less.
Yeah, say it.
Less.
Less than
Lesser.
0.5. So closer to 0 than 1. I know that much.
If the probability that we saw earlier was 0.45 or 0.46 or whatever,
Mm-hmm.
and if a probability of 0.5 is equal to a logit of 0,
Right?
then it makes sense that it will be a little bit lower than 0.
Yes. So we know a logit of 0 is probability of 0.5. This logit is below 0, so we're closer to the 0 side than the 1 side, but just a little bit. Yeah. Now, like I said, I can't do the math in my head, but Stata will do it for you. The word margins is used to generate predicted values. Normally, you say over a range of predictors that you want the prediction for, but we don't have any predictors. So I just write margins. It's like, okay, here you go. Margin is 0.45. That number look familiar?
So did it actually take the 0.2 whatever and actually transform it back to what we were actually wanting to look at?
Yeah, this is what it just did for us, this text box. E to the logit over 1 plus e to the logit. So the probability of apply being 1, meaning you're going to go to graduate school, is 0.45. That was the proportion of 1s in the data. Now I know my model is predicting the probability of a 1 and not a 0. Exactly. Now what would it be if it were predicting the 0 instead? What would this number have to be? What would it change to?
Inverse, positive.
Yep. The additive inverse, I've learned that is what it's called. When you take the sign off, multiply by -1. Yep, flip the sign. So that's why it's nice that logits are symmetric, because if you know one direction, you automatically know the other without having to do any additional computations. So -0.2 is the logit of the odds, the probability of the 1, which works out to be 0.5 with this handy-dandy formula. So, go ahead.
Okay.
Yep.
What's the rationale between, because I feel like we had 0.45 at the top.
Yep.
So why do we have to do all this again?
Fair question. This is why.
Okay.
So we can't, actually, no, let me go to this one. This is why. Because when we add predictors, we can't predict probability directly because they're going to go out of bounds. Like if we have a linear slope of x, it doesn't know where to stop. What we need is a nonlinear relationship between probability and x. And the way we get it is I literally generated this with a logit slope of 1, then back translated the predicted outcomes and make this graph.
What's that process called? That step called?
The back translate is called an inverse link function. So link is going from data up to model. Inverse link is going from model back down to data. To use the example I gave before, I have this sweater costs -0.2 in Kohl's money. I beep the price tag, my inverse link function machine, and I find out the actual price is 0.45 in real money. That's how I think of it. So logits are like this imaginary continuous thing. It's just a nonlinear transformation of this probability. So the model directly predicts logits. It indirectly predicts probabilities.
So, just make sure I'm not tripping. So the reason, we just happen to have the 0.45 just happens to be within bounds, but there are times when it's not.
No.
And the reverse function would be?
No, if you inverse link, you are guaranteed to keep the probability between 0 and 1.
Okay.
Guaranteed. And that's why we do it. So the 0.45 is what it has to be because that's what the original mean of this variable is in the data. There were only 2 possibilities as to what result I could get, 0.55 or 0.45. And now I know which way is up. Remember like the first week of class when I said the hard part is going to be figuring out what the hell y is? This is what I meant. Like what are we predicting? Logits. What is that again? Oh, it's the log of the odds of the probability of a 1. What? I know. Once you get that straight, though, the rest of it is the same. So I did the same thing in R. So your syntax for R, I am using a base R package. I didn't need anything fancier for that, called GLM. And by that, they mean generalized linear models, of course. Although you can fit standard regression models using this as well, but people don't bother. So it wants to know the name of my data as usual. Formula, which means model as usual. So note, I'm not doing anything other than saying apply to is the column where my 0s and 1s are stored. And I just want one fixed intercept in the model. The 1 doesn't have to be there, but I put it there for my own use to remember that it's there. The new part is this piece right here. Family equals binomial, in parentheses, link equals logit in quotes. So Bernoulli is a special case of binomial. Binomial is for multiple trials, and you can have a success or failure on each trial. Bernoulli is one trial, with one success or one failure. So binomial is a more general way of just expressing it. So then R says, intercept in parentheses is -0.2. So R is doing the same thing. Hooray. Question.
How do we know R, GLM, is greater than 1?
You don't. That's why I did this.
Oh, so you don't know until you intercept. And the intercept is what tells you.
You would have to find in the documentation where that is explained, and good luck with that. Yeah. Mm-hmm. And I would think the one is a more common default, but I know of zero packages like SAS, Logistic, or Glimix uses zero as the default.
So we didn't need that second step last semester or whenever you took before because the default is linear regression, no link function.
An identity link function.
Or identity link function.
That's
sorry,
right.
but yes.
In standard general linear models, regression and ANOVA, which are both for prediction, that uses an identity link, meaning times 1. So to get from model scale to data scale last semester, times 1. Never brought it up. Didn't need to.
So the way you can check that part is you run an empty model, and you find the intercept, and then you just look at your data set to make sure that you can see what, like, you physically look at the data and maybe you run like a
Descriptives.
average
Yep.
function in Excel to see what it gives you.
Yep. Yep, you can run descriptives. So here's what it looks like in Stata. I use the psych package and the describe function in R to do the same thing. And yeah, this is my answer key for what the software must be doing.
So if you found out it was reversed,
Mm-hmm.
would then you just reverse the values in your original data set to match the software, or would you just reverse your predict? So if you were predicted 45, you just need to subtract it off of 1. Which one is better?
Okay, so if I found out it was predicting the 0 and I didn't want it to, is the question. The options are find, in order of what I would most prefer to do, find some option in here that changes that. So I'd go to the documentation and start digging, which is what I had to do for the ordinal models that are coming up. It's even more fun in that case. If I couldn't figure out the option, I would take my entire set of coefficients and flip their signs. Because if I know that this is predicting the 0, I flip the sign, it's now predicting the 1.
And not worry about it.
And not worry about it.
Okay, very good.
If I change the data, that would probably be more confusing down the line because you're thinking about predicting this event and not the event is not what you wanted.
That's why I was. Okay.
Yeah. Changing what the software does would be my first step. Okay, so we got it. We know what's up. How about some slopes? We can do it. We can do it. All right, so I'll say that other things that show up on this output here, this is default summary for these models. I wrote a function that packages it a little bit more neatly. We have null deviance being 550 and residual deviance being 550. This is the log likelihood for the current model is the one we want to focus on, times minus 2. So R spits out, this is the number you would enter into your homework to check if this is the right model. Residual deviance is what it's called. Residual deviance, that's your answer for your homework. It's for your model minus 2 log likelihood. Now, I couldn't find an easy way to make R spit out probabilities, so I did it myself. So this is the shorter version of the formula. It's e to the logit over 1 plus e to the logit. The alternative version of that same formula that is shorter to type is this one right here. This is what I just programmed into R, is this formula. So I have 1 over 1 plus e to the minus 1, and then coefficients model to empty is the list of fixed effects. So in this case, it's just the fixed intercept that's sitting in here that's been stored by R. So it's going to do the math and print it, and lo and behold, 0.45 is what I get. Okay, let's see some predictors. So a main effects model, meaning each predictor without an interaction term, because this is hard enough, right? You're like, what? You're going to do interactions with logits? Are you kidding me? Yeah, we are. Bring it. So I'm predicting the logit, the log of the odds of the probability of going to grad school. That's what I'm predicting. And I'm predicting it from a fixed intercept, which is going to give me the expected outcome when all my predictors are 0, as usual. Beta 1, which is going to tell me how GPA affects the probability of going to grad school. Beta 2, which is how whether or not you have a parent went to grad school. And beta 3 is if you went to private instead of public university. So in stata code, let's see, do I have the R of both? I think I do.
Just as like an
Yeah.
interpretive question.
I do have. Go ahead.
It seems like a lot of these could be related to socioeconomic status.
Yeah, they would.
But they didn't put that in the model.
They did not, because I'm pretty sure this is fake data, and I don't know what a variable for socioeconomic status would look like, to be honest. Like a proxy for it, maybe, yes, but
It's multiple ways to define it.
yeah, they just made up some stuff. I'm quite certain, but yes. So the question then would be, to what extent do each of these 3 factors uniquely predict one's probability of going to grad school, wanting to go to grad school? So I put them in to my logit command the same way I would for a regress command. C dot means treat them as continuous. It's not strictly necessary, but sometimes it is. I am also storing the results of this model for comparison against other models. I'm calling the name of this model main. Okay, let's play interpret time. The intercept is right here, minus 0.54. Who's feeling brave?
People are not likely to go to grad school, less than 0, or to want to go to grad school, when their GPA is right above 3, and what did we center
Grad 0 means their parents do not have a graduate degree.
and their parents do not have a graduate degree, and I assume private is 1, so 0 is public school.
Yep. Yep, the predicted logit of wanting to go to grad school is minus 0.54 for somebody with a GPA of 3 whose parents didn't go and they went to public school. Yep.
And that's lower than the predicted probability.
Yeah, it's lower than the marginal probability. Mhm.
Okay, because now we're taking into account some of the other things.
Yes, we are adjusting our expected probability, our expected value, based on these other 3 pieces of information.
So does that tell us then something about our data? Does it tell us that in our data set, more than half of the people either have a GPA above 3, have parents who went to grad school or went to private school?
I think it would be hard to extrapolate what the distributions of these predictors are just from this result. If I had mean-centered each of these things, then this would be very, very close to the mean that we saw before. But mean-centering binary variables is weird, and I'm not here for that. Yeah, so GPA of 3 is probably average to a little bit below average. The zeros for the others would put them a little bit below average. So it sort of makes sense that it's bringing the predicted probability down with it. But yeah. So the intercept is still the expected outcome when your predictors are 0. It's the expected logit outcome. That's the kick. Now the good news is slope rules haven't changed. What's a positive slope mean? As x goes up, y goes a positive slope. As x goes up, y goes up. Negative slope. As x goes up, y goes down. Negative slope is the disco one, going in opposite directions, staying alive, continuing. So same here. My logit goes up if my GPA is higher. If my parents went to grad school, my logit goes up. If I went to private school, my logit goes up. Now we look at the significance values and put the coefficient in the sentence. I would say this slope is significantly positive if we use a traditional level of alpha of less than 0.05. It meets the cutoff for that. So for every additional unit of GPA, so if I move from like a B average to an A average, my logit of wanting to go to grad school is higher by 0.55. If my parents went to grad school, my logit of wanting to go also is significantly higher by 1.06. And if I went to private school, my logit is higher by 0.2, but non-significantly. So non-significantly positive slope here. So that part's the same. It's just you're predicting logits.
Can you please remind us with the cons being adopted here? We're interpreting that inversely, right?
No, I'm keeping the sign on here because I want the probability of a 1 as what the model is trying to predict. And so this is the like baseline value essentially. Yeah, the fact that it's negative doesn't change the fact that we're predicting a 1. Yep, in these data, 1s are less common. 55% are 0, 1s are 45%. Hit me.
I just want to make sure. So for every additional, like for the GPA unit of GPA, the logit goes up?
Yes,
It's not every additional logit,
right. Every additional unit of GPA as the predictor, the logit of the outcome of going to grad school goes up. Yep, by whatever, 1.55. Yep. Now this constant thing, it has a hypothesis test too. Do we care about this? The p-value is 0.06. Oh, it's marginally significant, approaching significance, trending towards significance. Do we care about this?
No.
No. I would say no. Why would you say no? Zoomers, you can play too. Yeah. So each of these coefficients, each of these estimates, is being tested against 0 as a null hypothesis by default. So it's telling you how far away from 0 each of these numbers is. So this is 2 standard errors away from 0. This is 3.5 standard errors away from 0. This is 0.66 standard errors away from 0. And this is almost 2 on the other side. But what does 0 mean in logits? Yeah, 50-50 probability. So this is almost not different than saying the reference person has a 50-50 shot. I don't care about that. One might, like if you wanted to say like for this kind of person, is their probability different than 50-50? That might be a question you'd want to know, but I don't. So I wouldn't worry about significance of intercepts or constants in any context unless you want to know if the predicted outcome being not 0 is something you care about. Like a mic drop. So how well did our model do? We'll foreshadow for next time.
We haven't answered the question.
Yeah, well, we answered the question, but did we predict this outcome significantly, do you think?
Oh no.
Maybe.
Marginally.
Yeah, so how much R-squared did we get? How much variance did we explain?
We didn't care.
It's
don't
gone.
know.
We don't know. And as evidence of that,
There's only a chi. I was gonna say I saw a chi.
there's something called pseudo R-square. Does that inspire confidence when you see a prefix of pseudo or quasi or anything that means ish? R-square ish is 4%. Yeah, we don't have an E. That's going to be the tricky part. In all of these equations, there's no E. It's gone. Do you remember why?
Focus on the logic.
Because it's a binary outcome. So in the Bernoulli distribution that requires logits, there is no separate variance. That's not a thing. It's only a separate thing in normal. So if my predicted probability is 0.5, I know the variance around it is 0.25, the end. If my predicted probability is 0.8, I know the variance around it is 0.16, the end. So not only are our errors not normal, the variance in them is not constant because it varies directly as a function of the predicted mean. There is no R-square. So we're going to have to come up with some alternatives to think about effect size and how that works. And those are called odds ratios. But that's for another day. Okay, recapping. What do link functions do? What are they for?
Transform the conditional mean.
Transform a conditional mean to be predicted so that what happens in the original data? Here's your clue. Boundaries, yes. So that the predicted probabilities stay between 0 and 1 like they're supposed to. That's what link functions do. Okay, hang on to that. Other questions or things you want to review in a minute? Yeah, all right, I'll let that sit. It will get better with practice, I promise. I know it's a lot right now. I know. I'm not going to lie to you. It will get better. All right, so you can work on your next bridge activity. You can start on homework 1 if you're feeling extra ambitious. Let us know if you need anything. Thanks for being here. Stay safe tomorrow. Hope to see you Thursday. Maybe in person, maybe under snow. Who knows? We'll find out.
I saw happiness when I looked at your example.